Well, good morning, everybody. Thank you for being here on time. We've got a very full program, and I need to get through these first few minutes relatively quickly to give the time for the important speakers. My name's Craig Priest. I'm a professor here at the University of South Australia and director of the South Australian node of the Australian National Fabrication Facility. You'll hear a lot about what that all means during this winter school. In fact, you're going to be immersed into the capabilities and with the team of ANFF-SA and also OptoFab and a range of excellent people from 3 different universities here in South Australia and also around the country, as well as industry experts. It's a very exciting school. We put a lot of effort into it because we wanted to make it the very best possible school that you could possibly do in the middle of winter while it's, 12 degrees or something outside. So you're in the right place. You'll be warm and interested and hopefully a little bit entertained, but also you'll be able to network and enjoy and meet and greet. So let me just kick off. Hopefully my slides work. Let's see. There we go. One important thing that I would like to start here is just to acknowledge the country that we are on. The land that we're on is, of course, the land of the Kaurna people here in the Adelaide Plains. We acknowledge their traditional connection to that land over many, many years, and we respect their spiritual relationships with the country. Here at UniSA and all the universities and all the organisations involved have a deep respect for the long history that the Indigenous people have had with the lands we're on here, but also the lands of those who have come from far to join us today. And so we acknowledge that this morning. A couple of little housekeeping things. I hope there's no emergency, but of course if there is an emergency we need to know what to do. You are at this star at the east end of the MM building. If there is an emergency, we can go straight out the doors out here and around to the grassed area that you'll see. There will be people with hats to guide you. There will be the building talks to you if you're in the room here, and so just follow the instructions of those around you and what the building's telling us to do. So just keep that in mind. The grassed area is where we go. This is a microscopic toilet. I can assure you that we've got much larger toilets here on campus as well, and in fact it's right outside the lecture theatre, so I think you'll have no trouble finding them. So for all of you in the room, as well as many people who are online from all over the world, what is this winter school all about? Well, for us, it's really something that we're very passionate about because we want to inspire careers in this area. We want you to know the facilities that are at your fingertips so that you can do your own innovations. And we want to engage and inspire you to be innovators as well. And you'll hear in the first talk just how important innovation is in our society. There'll be insight presentations from national leaders, and there's lectures and practicals by technical experts. And they're genuine technical experts, and these are genuine leaders. We've drawn the very best from across the country and internationally to be in front of you. So really lap up that opportunity, talk to them in the breaks and make the most of every moment. In fact, I've just seen Paul there. We've even got somebody from all over the other side of the world, Paul, to join us to speak to you. So many things to look forward to. We've made sure the content is introductory and accessible for you because we've got a room full of people with many different backgrounds. We want you to be able to enter into this area easily. And so ask your questions. Don't be afraid to do that. The ANFF, the Australian National Fabrication Facility, is part of the National Collaborative Research Infrastructure Strategy, a federal government initiative, very strongly supported by the state government and the university sector as well. And what you see here on the map is 8 nodes of ANFF around the country. And of course, here we have the South Australia node being led from UniSA in partnership with Flinders University. And we also have at Adelaide Uni part of the OptoFab node, which you see is led out of Macquarie University in Sydney. Here on campus is, obviously you're at UniSA, you would have worked that out to be here, but we have the Future Industries Institute, and much of what you do in terms of the practice will be done in the labs of that institute. We're UniSA is leading research institute in this field. The Flinders University has 2 key institutes, and you'll hear more about them in some of the presentations later in the week, but the Medical Device Research Institute and the Institute for Nanoscale Science and Technology. And so you'll get to interact with people from these facilities, and I just want to thank those who have been drawn from both of those sites to help today. Meet the ANFF-SA team. Please do that. Make yourself familiar with them. There's a whole bunch here of amazing people to talk to and to meet, and they've got many different backgrounds, so I'm sure you'll be able to find somebody who's of interest to you. So that's one of the key things for the school. I mentioned before the people who have come from far and wide to make the school happen. This is a one-shot slide here I just realised I might minimise that. Nobody in the room wants that on the way. So we've got all these different companies and agencies and universities working together to make this school, and so thank you to all of those who have contributed from many, many different places. Is that where it should be, Belle? No. Oh. Okay. This is what I wanted to show. So tomorrow night you'll have an opportunity to visit the OptoFab node at Adelaide University, or I should say the University of Adelaide, especially while we're doing a merger. I will never get that right. Soon to be the Adelaide University. So the University of Adelaide is hosting us very kindly there. There'll be, I think, pizza. Am I right? Pizza. There's certainly some food there, and so join that tour. Speaking of tours, very briefly, hopefully I'm not going to run out of time here. There are some tour sheets around here, mostly full, but not quite full. If you're from interstate or overseas, we're going to give you priority because we know it's hard for you to get back here. So if you want to go on the tour, get your name down there. If you're a local, feel free to put your name down, but if we bump you, we'll make sure that you've got another opportunity to see us in the near term. So, thank you to the sponsors that we've got here, and you're going to hear more about them as we go through. And is that all to know? No? Okay, coming back to that. But for now, we're going to move to our first speaker. So I'd like to invite Jane Fitzpatrick to join us. Jane is the CEO of ANFF and nationwide, and has come all the way to Adelaide to join us for the school and to welcome and open the school. Jane is fantastic. Should I read some of your... No, should I? I might. So Jane is an amazing leader of ANFF, and even for her to spend time in Adelaide, especially to be a part of the school, we greatly appreciate that, Jane. She's held positions with academia, medtech startup and space industry focused on research entities, as well as board positions for women in technology. She holds a PhD in applied immunology and a degree in biotechnology, and added technical expertise in many areas, including micro nanofabrication, and is a fantastic leader in science and technology and innovation in Australia. So please welcome Jane.
Thank you very much, and it is absolutely wonderful to be here again. I try and get down to this every year if I can. And I'd like to also just acknowledge the country in which we're meeting today, and also acknowledge the fact that we stand on 60,000 years of engineering and science before us. So we're just continuing that tradition that the people of this country started a long time ago. And I've just got a couple of slides. I was going to go off the cuff, but then I thought, nah, pictures are much better. We good? All right. So Craig mentioned very briefly that we are the Australian National Fabrication Facility. The purpose of the Australian National Fabrication Facility is to provide services and kit and expertise to everybody in the country to enable them to do micro and nanofabrication without having to become the experts on day one. We're the experts on day one. We'll get you to be experts on maybe day 200, but we'll get you there. So we'll allow you to make sure that you access those capabilities and do what you need to do in your projects to make your project successful as quickly and efficiently as possible. All those tools are there. Everything is part and parcel. You can see here, these are all the universities that are our partners. We also have, obviously, all the partners of the state governments, and you will hear from your state government very shortly. What is NanoFab? You're going to get much more information than this in the next week, but this is my shortcut slide that I use for people who are not going to go into the kind of things that you're going to learn in the next week. In general, when I'm asked what is nano and microfab, well, you start with a flat surface, you add bits on or you take bits off and you end up with a 3D structure. That 3D structure has a function. That function is what you're aiming for. So depending on what you're doing, depending on what those layers are, depending on how you've done that patterning, deposition or etching, will give you a different function at the other end, and that's that functionality that you're really aiming for. And we do that in a lot of different ways. Right here this week, you're going to be exposed to a number of the different capabilities that do that patterning, etching, deposition. But we have about 500 different capabilities across the country, and you're accessing those through the network that is ANFF. We do this through training, direct access, fee for service, so if you just got a design, we will actually go and make that for you, and also project advice and consultancy. And for a lot of our undergraduates, postgraduates and postdoctoral work, clients, that project advice and consultancy is really important. We can sit down with you and actually look at your project and figure out how that project's going to work on our tools and how you can get the best out of it. So, do we do this well? Well, we think so. These are some of the numbers from 2023 as to how we've actually achieved our goals in helping people on these tools. So over 24 years of tool usage, that's 215,000 hours, over 3,000 clients, over 3,000 training instances. So that's how many times we've sat down with somebody and taught them how to do something. That's an incredible number of things that we have trained over the last year. 600 publications that actually mention ANFF. Not the ones that we've actually supported, just the ones that we've actually managed to get them to remember to say we helped. And then there's over 20,000 items manufactured and actually sent to clients. So this is a big organisation that does a lot of different things, and they're right at your fingertips. So how do we, or why do we exist? Well, we exist because we help the national agenda. We help the national science priorities. We help the national innovation priorities. These are just two of the current strategic priorities from this federal government, and I've just put ticks against the areas in which we provide most value. I'm not saying we don't provide value into the others, I'm just saying that I can pick out really good case studies right now on all of the ones with a tick. So the NRI roadmap is the National Research Infrastructure Roadmap. So this is our guiding document as to what infrastructure this country needs to perform on an international basis. What do we need to make sure that we can compete with the rest of the world? And you can see there it's to support those particular research areas and those innovation areas. The National Reconstruction Fund is about building our capabilities in Australia to be a manufacturing powerhouse. And as you can see there, we also add an awful lot of value in the areas of priority there. So the federal government, the state governments, the universities pour money into this so that you get access to the people and the tools that get your research to where it needs to be. This is an incredible program and one of the most unique programs in the world when it comes to research infrastructure. And this happens not just in micro and nanofabrication, I will mention, it also happens in microscopy, astronomy, urban databases, environmental monitoring. So there is a huge amount that's not just in this area. So if your research area needs help in a research infrastructure, there's probably an NCRIS capability that can come and help. And these are the people that help. Tools are great, but they are paperweights unless you know where the on button is. Okay, these people not only know where the on button is, they know where the off button is, and they know what's happened when the error 405 comes up. All right, so these are the people that actually make sure that your project is a success at the back end. So all of these people, you'll see some of the faces in that group that you'll meet this week. Find them, talk to them. These are the people who will help you. And if you go away from here and you go, I would like to get some more information on, or I didn't really catch something, we've got an online learning portal called ANFF-Enlightened. You can get to it through our website, so just jump on. It's there. It's a big button at the top menu. This has self-taught learning courses that will get you that information at that kind of high level that will allow you to go further and find out more of what you need to do. So feel free to jump on there, get some of the basics from some of the things that you didn't get access to this week, because you're here for 4 days. This is a packed 4 days, but there's so much more that there is out there, and some of that is available on ANFF-Enlightened. It's free. There, the button. That's where the button is on our website. The last thing I'm just going to mention is ANFF-SA. So not only are we trying to help the research projects get to where they need to go, what happens then? Research is fantastic. We do brilliant research in this country, but sometimes we stop and we fail to actually get those ideas onto market. So ANFF-SA is a small program that we have that allows us to give a little bit of funding, few small amounts of gifts, financial gifts, to projects to try and get them a little bit further along the commercialisation pathway or the translation pathway. So this is our initiative to try and get some of the research projects that we know have market potential, to actually give them a little bit of a leg up, to figure out whether they've got, to do a manufacturing feasibility study to show that an investor that this can be made at scale, or a market analysis to show that there is a market that will pay for this at the level we want that it's going to cost. So we're trying to do that with some of the projects going through. And with that, I'm going to stop talking and introduce you to your next speaker. Yeah? Okay, so I'm just getting the nod. So our next speaker is from the state government here in South Australia. Dr. Judy Halliday has been instrumental in supporting research infrastructure and shaping how that investment is coordinated, how that investment is going to bring value into this state. She has a long history in being a friend, for want of a better word, to the research sector and the innovation sector. And she's going to talk today about how innovation is essential in a complex and uncertain world. So thank you, Judy.
So my role here is to lift everything right up to the helicopter view of innovation, if you like. I will just point out that I do understand your pain. I have actually written a book chapter on micro and nano technologies in vaccine development, so I'm fairly familiar with the technical aspects of the sorts of things that we're going to be doing over the next few days. But what I want to do now is talk about things from a much higher level, talk about innovation. No, it's not going to let me do that from out here.
It should do. I tried it yesterday.
Now try.
Right. There we go. Before I do that, I'd also like to acknowledge that today we meet on Garniata. I'd like to say to all of you, Ninamani. Mani is the response. Ninamani is like a welcoming greeting. This has always been and will always be Aboriginal land, and I respect the cultures of the land on which we are fortunate enough to work and learn today. So innovation, kind of a contentious subject as it turns out. Probably the thing that we all know and understand, or we should know and understand and probably refer to, is the OECD's Oslo Manual. And the latest edition defines innovation for us. It's about improved and new products and processes that differ from what currently exists, that allow us to bring benefit to users or potential users. It's a bit more of an expansive definition of innovation than it used to be. It used to be very much focused on actually only the product, the process of making the product. Now it's a bit focused on the product as well. It's implying different types of innovation, all types of innovation, and I think for your purposes and for mostly for our purposes in the government around this sort of thing, we're really interested in product innovation and process innovation. There are many, many challenges ahead of us today. I think many of you will be aware of those. All of the sorts of products and processes that are going to be needed to address these challenges probably yet don't exist. They might exist in your minds in this room, and you may well be developing them as we speak. But we're going to need to develop a whole lot more products and processes around the energy transition, around dealing with climate change, dealing with health challenges. That's not too far in our distant memories to understand what was involved with that. So there is a lot of innovation required in order for us to continue to thrive and prosper on this planet. However, out of 43 countries, Australia is not in the top 10 for being an innovative firm, having lots of innovative firms that develop innovative products and services. As a percentage of total firms in Australia, about 21% would be considered to be innovative. Let's think about Canada as a good comparator for Australia. It's a similar sort of country in that, people kind of live around the edge and there's a lot of digging dirt up and mining and farming and that sort of thing. Canada's probably a bit more economically similar to Australia than some of the other comparative countries that you might hear about when we talk about innovation. The United States, for example, and particularly Silicon Valley, or Israel or other countries that are often used. Finland is another one, but Canada's probably a bit more like us. Now, in manufacturing, 51% of those 38 firms are making innovative products. In Australia, only 26% of our 21 firms are making innovative products. Now, you are here to spend a week, 4 days, immersing yourself in all of those innovative manufacturing processes, making new products around nano and micro fabrication technologies. So it's in your hands to help improve some of these numbers. It's even worse for Australia if you look around the services sector. We're performing more poorly there. Fundamentally, what that means is for us, we are reliant on others to provide innovation to us, and we pay for it. Now, you'll have heard, if you pay attention, really, if you don't pay attention, I suspect you'll have heard a lot of discussion around the reindustrialisation of Australia, turning us into a country where we make things. We were a country of makers. We've gone downhill pretty substantially very quickly in the last couple of decades, and that's something that needs to be turned around. You'll hear about it talked about as becoming better at manufacturing, having sovereign capability, holding our own destiny in our hands, all manner of different things. Fundamentally, what it means is we need to be better makers and doers. So, kind of why do we care? I've already talked about some of the greatest challenges and solutions that we're going to need for those. Innovation does a whole lot of things that make better and more efficient products and services that give us better outcomes, be it in healthcare, be it in energy, be it in mining, be it in space. Firms that are innovative create the sorts of jobs that you are going to want to have into the future. They're high technology, highly skilled jobs, and they also, firms that are innovative, contribute to economic complexity and resilience. And that's important in an uncertain world because, like diversity, the more economic complexity, which is just the business, I guess, view of diversity you have, the more you can go around being buffeted by whatever change or challenge exists. So Harvard produces what's called an economic complexity index. Canada is 41 on the economic complexity index. And I don't expect you to kind of learn or know or pay too much attention about the detail in that slide. But what I'd like you to look at is the number of different colours, how they are proportionally to each other, and the big and small boxes, the distribution of big and small boxes. This is Australia. We're 93rd on the Harvard Economic Complexity Index. I feel like there's countries not as good a distribution of the big, medium and small boxes. This is our challenge. This is where the building of innovation, capability, capacity and of firms that innovate and of people who make and do is really important for our future. This is I guess, a bit of a global view, if you like, by a group called Startup Length of Australia. It's innovation and entrepreneurship, and that is innovation and entrepreneurship is my kind of portfolio of responsibility in the South Australian state government. I'm really interested in research commercialisation. I'm interested in entrepreneurs, startups and scale-ups. So there is, and there has been, and there continues to be a bit of an emphasis on that kind of activity in Australia at various levels of government, because fundamentally, if you don't have those innovative thinkers, the entrepreneurs, people who are prepared to take a risk, start new firms, build new products and services, we're never going to get off the bottom of that economic complexity index, and we're also never going to get up into the top 10 for innovation. We're particularly interested, obviously, in Adelaide in South Australia. Adelaide has, if you can really find it, there has been steadily increasing its score, because we do like a league table, like everything else. It's going up the table, still in the 200s, but gone up 14 points or 14 places since the last time. So that's a good thing. What is not so great here is that there's a little bit of a downward trajectory for Australia as a whole there still. But notwithstanding, as Jane pointed out, the amount of money that the government's poured into various different things in various different ways, including NCRIS facilities and things like that, which includes ANFF. South Australia has, as I said, had a fair focus on this over the last 7 or 8 years. It's an emerging startup ecosystem. You have to have those kinds of ecosystems to put the supports around those creative and innovative thinkers, the entrepreneurs and the businesses which are high risk. So whilst it's a bit gloomy if we think about the macroeconomic circumstances, if you like, at 93 on the economic complexity league table, there is a groundswell of the foundational activities in this country and this state that will help build us up out of that. This is just another way of looking at our data here in South Australia around startups that have been developed over the last probably, a bit more than 10 years, 12 years. From 2012, you can see it was a bit scratchy around down there in the weeds. But as we've gone over time and into 21, 22, 23, so in that immediate post-COVID phase, quite a bit of growth in the sector, growth as measured by investment. Investment obviously then is a proxy for growth in the sector. So that's kind of the end of my very high-level discussion about things. What I thought might be interesting to think in a long-term historical context is where would we be without nails? Not quite micro or nanotechnology, but getting a bit smaller than what I've been talking about. So nails have been around in pretty much the same form for thousands of years. You know, a nail from 2,000 years ago doesn't look hugely different from a nail from yesterday or one you get buns down the street. But if you think about it, more than 2,000 years ago, archaeologists can tell us they found 7 tons of nails when they dug up a Roman fortress in Scotland. Now those nails would all be made individually by hand by blacksmiths. Now I don't know how your imagination works, but I'm kind of a visual thinker, and I'm trying to imagine what 7 tons of the NVIDIA chips would look like nowadays versus 7 tons of nails, and the cost and complexity of those 7 tons. So really important activity, that making fundamentally important, very small components of a larger thing, the nail. Automation really only came to nails in around the 1600s when they started to kind of put tools on benches for blacksmiths to allow them to make more nails a little bit quicker. The sorts of nails they made are those little ones there that you can see in that picture. And then through the Industrial Revolution, pretty much the whole thing was automated, and there was introduction of new materials. So steel nails became a thing. Before that, they were very much probably made from iron, in some places copper or other alloys, but really whatever mineral you had available to you in the local area that you could make into a metal of some form and make a nail. So they become much more standardised small things that you make, but the fact that they can persist through many, many years, those things that are fundamentally important for our survival, if you like, will persist through centuries. Not sure about the NVIDIA chips, but who knows? Hopefully you guys are going to be making new and important things and learning a lot about how to make those things in the next few days. Thank you.
You can see Judy comes with an incredible breadth of knowledge of the field, and one of the reasons I wanted to start with Judy's talk is to give you that context of why innovation is so important and why it's so important that in schools like this, where you spend 4 days immersed in the technology, hopefully it'll spark ideas. And we know people who have come back. One of the successes that we had, which we intended right from the beginning of the school, is that graduates from the school would come back and be speaking at the school, using the facilities that startups would be forming. We've seen that over the years, so that's potentially the future for you. So please be optimistic and engage really well. Are there any questions for Judy?
Well, anything, ask me anything.
Can I ask a question? Okay. Given that we've got such an international collaboration here today, how can our participants, both here and online, make the most of it?
Well, kind of collaboration is the thing that overlays success in innovation. You know, it's a team sport. It's a very hard road to hoe. And finding the people that help you, who have got skills that you haven't got, who've got knowledge that you haven't got, who've got connections, money, all of the things that are needed for success is really important. And so collaboration is absolutely one of the key ingredients for success if we're going to convert our country. And arguably other countries are interested in this too. I mean, I don't think it's just an Australia or just a South Australia thing. I think that the global challenges that we all face are global challenges, and therefore collaboration is to be encouraged and supported.
Any other questions? I've got one. Somebody else. Oh, there we go. Yes.
Well, thank you for your insightful talk. What was your transition from academia to the government sector?
I spent probably the bulk of my career in the private sector. So I did have an academic career. I did a PhD in bioinformatics. I had a research group up at UTAS, was going down a research career path, and then stepped out into a startup. Engaged with new things, was in co-invent companies and what have you, in startups at the time. Came down to South Australia from Queensland in the beginning of 2017 to help the state government set up some early stage funding for innovative and collaborative businesses, entrepreneurs and startups. And so have been leading that team that was then brought into government at the change of government and the little part of government in South Australia. So I've got a team of people that do things like work with researchers and ANFF and other interest facilities around translation and commercialisation, work with universities around translation and commercialisation, work with startups, and we support the startup up here that some of us done before. We have a team that provides grant funding, assessment of grant funding directors to the startups, and probably about another 16, 17 programs in that kind of innovation space. So I did the academic research at then moved into business, learned on the job, which is probably not to be recognised. Editors do, well, you do the both. Formal learning and learning on the job is probably a good combination. So working in a startup company that we actually listed on the stock exchange, raised about $150 million that business in a way. And then helped form all our top startups at universities to invest with you before moving on to state government. So I feel like I'm on my about 6 years.
Yeah, I'm just going to follow up. One of the things that both Judy and I come from a technical background, and we've ended up in a non-technical field, but I can guarantee you that everything I've learned through all of those different
not afraid to take a bit of a risk. Sometimes moving from one career path, you're in a really good position, you've got a postdoctoral career path ahead of you, looks like you're going to get into some kind of full-time academic research career. Fabulous, that's a great career path. The opportunity to step out of that and build a business just seemed like something that was interesting and exciting. And like most entrepreneurs, I've asked myself a number of times before doing something arguably not that smart, is how hard can it be? This might not be so difficult. Of course, we all know that's not quite how it turns out. But I've always really enjoyed the opportunity to try something and learn something. So it wasn't, for me, it was being about being receptive to opportunity rather than consciously making a decision to change. There were some elements of it, I think, I'm not, I think I can do something. And I've ended up in government and policy, which is, interestingly actually, early in your career, you kind of focus on your own achievement, your own success. So ego drives that a little bit. I'm a bit later in my career now, and I live vicariously through the success of others. I'm quite happy to enable all of you to be successful rather than me.
Yeah, two questions just behind you.
Why do you think Australia is so far behind our innovation index?
I don't think that's actually an easy question to answer. I think fundamentally there's many different things. One of the things, globalisation didn't work in our favour. Cost of employing people in this country was really high. We've always had a pretty high standard of living, and so cost of employing people to make fast-moving consumer goods just doesn't make sense here. What we haven't done, so we kind of lost sight of the ability, the importance of the ability to be makers and creators in our own way rather than buying it from somewhere else. Because it was cheaper and potentially easier to get it from somewhere else. I think what we realised over time is that whilst automation actually is our friend in this regard, because pretty much all of those very routine jobs that might exist are being automated away. Now, people are worried about that, but the reality is that creates lots more jobs in kind of understanding how to use that to make better products and services. So I think we had a bit of a took our eye off the ball moment. It is hard to deny the sugar hit you get from selling dirt at a premium price, or grain or whatever it might be. But at the end of the day, that means you buy it back at a more premium price. And so, we need to think about that perhaps. And that's just a very small amount of the many different factors I think that have inspired against us over the years.
There was one more question. It's a library in you mentioned that Australia is not necessarily a place of economic capacity. Is there any plan to improve the economic complexity of Australia?
So there are, all of the kinds of things that would occur around the future made in Australia kind of legislation that's maybe going to pass through the Parliament sometime this week, who knows. The National Reconstruction Fund, the IGP, what's the acronym stand for? Industry Growth Program. So many acronyms I use that. So there is an understanding that we do need to make more value-added goods. We need to convert the iron ore that we dig out into green steel, for example. There's an intentional focus on doing that. We need to focus on the energy transition and selling our excess energy, because renewable energy in this country is a massive opportunity should we be able to capture it appropriately. And we can sell that energy, which is a value-added product, then to other places. So there is a lot of attention being paid to the need to kind of elevate our economic complexity, build new and interesting businesses here. All of you are going to be concentrating on making very small things, which are unlikely to be very small things that you'll make billions of, unless we go back to our NVIDIA chips again. But things that you will make, maybe thousands of at a premium price, or tens of thousands of at a premium price. And that's kind of the sweet spot for us in Australia, is to make complex things where people pay a premium price.
one more question.
So hearing that you're involved with policy, do you see a shift in how Australia is looking at resources, management, conservation, and protection of the environment related to what's produced and then what the outcome is to deconstruct whatever's produced?
Yes, is the short answer.
Great. Thank you.
Government considers what we always think about when we're creating policy, what are the wider economic benefits. And by that we mean all of those kind of ESG things. Government is concerned that policy not only gets us economic complexity, it helps us preserve the environment, it gets better community outcomes. Now, arguably, not very good at it, but intentionally trying to do that over time is very much part and parcel of policy development in any field of government work. It's not like, we're not like venture investors in a new technology. You know, we don't need a 10 times economic return in dollars. We would like some profit, but we would be much more interested in profit plus community, environmental and social outcomes.
I might just indulge myself as the chair of this session to ask a question, Judy. And, the team here around the tables are going to be immersed in a nationally significant fabrication facility this week and get their hands on equipment and devices and all sorts of things. Can you say something about how important, I guess, research infrastructure and that type of capability is in that picture that you're painting of us emerging from our current ranking into an innovative society?
I think it would be fair to say that it is fundamental, it's foundational. You can't build more economic complexity, more complex manufacturing, better manufacturing, new products, services and processes without fundamentally access to all of that infrastructure, both the equipment but more importantly the people. People understand the power of the equipment that they use, how to use it to its best effect to get best outcomes, how to interpret data and information they get from that equipment. You know, the Commonwealth Government has over many years invested billions of dollars into, nationally significant research infrastructure across Australia. ANFF is one part of that, or one project within that. The state government here in South Australia has invested to date more than $60 million in a small number of those things to underpin particularly our manufacturing capability and capacity. I think the challenge always is the time taken from a great idea and we're going to start making things and doing research and developing a new product and service is long. 7, 10, 15 years to go through that whole process. It's tricky in a political cycle of 3 to 4 years. And so really I think the frame of reference doesn't really matter which political party you are. Everyone I think understands our need to build our capability and capacity. They just use a slightly different view of that frame of reference for that.
Excellent. Well, thank you very much. We've got a small gift for you, Judy, so thank you. So let's put hands together for Judy.
And I really hope you have a great 4 days. Unfortunately, I have to race off to other things, but I'll be looking forward to hearing from Craig and Jane and Belinda and others about how fantastic the whole experience was for everyone. Have fun.
Thanks again. Now, one of the bingo games we can play this week is how many times I can get to Judy to gift to the speaker. I'm notoriously bad at this. So,
I just wore the tape strong.
if I can get one by home. But I do, Jane, can I just ask you to come up because I did forget the first two. Anyone who can tell me how many times I forgot at the end of the week, we'll find something quick. Let's thank Jane as well. So I think you've already got a flavour of the calibre of speakers that we've got, and for Judy to give that big picture. The other insight talks through the week are going to drill down a little bit more into more specific areas. We've got leading academics, leading industry experts, as well as leading government people to speak to you in these insight talks. Now, the idea of an insight talk is not to teach you every equation that's required to do the things that we're going to talk about. It's to show you what can be done with these, microengineering and microfabrication. And so we have speakers in different fields. One area that's very close to my heart is microfluidics. It's the area of my own research, but I spare you me speaking on this. I've got somebody much better who can speak, which is Professor Michael Breadmore from the University of Tasmania. Michael has won fellowships, national fellowships, competitive research fellowships. He is prolific in publishing in the field. He leads a very strong and internationally regarded group, and he's also representing us here as Australians on some very large international scientific communities. And in fact, was instrumental in bringing some conference, which I probably can't mention because it's still not announced, but to Australia very soon. So it's very exciting to have Michael here in person. He's very busy and can't always be here in person, but here he is. And so, Michael, we're looking forward to hearing about microfluidics from you. Thank you.
Just bear with me 1 second. I've just put the camera on and now I've messed up the screen. Can I borrow you for 1 second?
Can you borrow me? No.
Yes.
What have you done?
I wanted to put the... Do you turn that?
Yeah, pad, Craig, pad. Come on. Conference. Yes, you can tell them.
I want that one. Because you're going to walk around, aren't you?
Yes.
But now I can't.
What do you think I do? I don't work here. What's up my desk?
Okay. Why can't I get this out?
Anyway.
Sorry. Hang on, just hang on 1 second. I've got a little technical issue going on here.
That's all right, I'm padding.
Great.
I'm padding. So,
Okay.
he had an ARC, he was an ARC future.
Sorry.
Let's just see if that works.
Australian Post.
Right, we're done. You can stop now, Craig.
Thank you. He has chickens.
You can stop now.
And a garden, and I've known Michael for years. So, Michael, you can stop now.
Thank you, Craig. Good morning, everyone. As Craig said, I'm from the University of Tasmania. I live in Hobart. I'm from Halliday country, which is Tasmania, and I would like to pay my respects to the Kaurna people who stand today, but also the Palawa people, and also the people whose work, the lands of who work on the future today. I'm not quite sure how I followed Judy. That was a wonderful talk. Hopefully that's inspired you to actually want to innovate and, make Australia a better country. What I'm going to try and do is perhaps show you one avenue of which you might be able to do that through the field of microfluidics. So the winter school here, you're going to learn about how to make stuff. Microfluidics is what you do in the space between the material. And typically fill that with fluids. Fluids might be gas or it might be liquid. And you can see this picture I've got on the slide here. This was one we made in 2014 with our crowd-funded 3D printer. It cost me $2,500 at the time. I'm super excited. This has got 1,500 individual fabrication steps. So when you go through some of the workshops today and you think about making a layer of something, then think about making 1,500 layers of something, and then think about how you might do that. So I know you're going to have a talk about 3D printing. I love 3D printing. This is not the answer to everything, and you'll hopefully learn that through the workshop. So where did microfluidics start? Well, it started somewhere in about the late 80s, early 90s, by a person called Andreas Mons, who was working in a company called Halliday in Switzerland. So it's really interesting that this innovation has come out of the industry here, not the academic people. And the proposition was really simple, right? We know how the world changed when we started to make microelectronics with silicon microchips. Could we take exactly the same concept and do it for chemistry problem? So can we take the stuff within a lab? Can we put a really small, highly integrated thing called a chip? Just like a silicon microchip, but instead we're doing chemistry and we're doing fluids and biology in those devices. So this is Andreas with one of his little devices. Actually, in that plastic bit, it's an even smaller bit of glass. And the idea is, in that piece of glass, you have a whole heap of processes that you would normally do in a chemical laboratory, all done in this really highly integrated, simple device. That's really good because it means that we can do things quickly. And this is one example from the very early 90s of why we wanted to do things figure on the right here is a map of those amino acids every 20 seconds over 30 minutes of what's going inside a rat's brain. Right? So we're able to use this technology to monitor the brain chemistry real time. The rat is perfectly fine, maybe not perfectly happy, but it is alive, it's surviving. And you can see that around about this 10-minute mark, I think about 12-minute mark, so there's an infusion of GABA, and that causes a whole heap of responses in the amino acids going to the brain. So we can now understand brain chemistry because we can do this highly integrated measurement in a really quick format. Why would we want it to be portable? Right? So one of the advantages of making it small is we can take it everywhere, right? You guys are probably too young to remember life before mobile phones. Where you had a landline, you might have seen them on television. Some of us might be old enough to remember the first mobile phones were about the size of a brick, probably way about the size of a brick. And now we've all got them really small, right? We just throw them around everywhere because they're super light. We drop them and we die because they don't smoke, right? That evolution in technology to portability, why is that useful? So one of my favourite examples of why we want to make chemistry portable, and that's to send it into space. So if we send it into space, and this is particularly looking at amino acids in Mars to answer that really critical question that everyone wants to know, is there life out there? So if we can take something and send it to Mars, we can actually find amino acids, right? Problem is, it's really expensive to send stuff to Mars. So if it's really heavy, it's not going to go well, right? So you want to make it really small, you want to make it really light, so that you can get it there and answer the questions you want. Right? So size is really important. One of the things that we often don't think about, though, is this little thing that we've made. How do we use it? And this is called the chicken and lab syndrome. So you can see the guys on the right there, they've got that little thing on the microscope, and they need, the world around to actually power that little business. So what hopefully you're going to consider now is not just the little thing you're going to make, but the way in which you package that up, the way in which you put everything together. And so one of my colleagues at the university has been looking at how you integrate different functionality into the way you make something. So in a single step, you actually now start to have different material properties, and those different material properties allow you to do different things depending on what the material is. And that simplifies the fabrication process, but it also simplifies the stuff that goes around a little bit in the middle. Right? So we want to make things really simple, because when they're simple, they can be portable, they can be reliable, and we can do wonderful things with them, and you can be rich. I want to be rich, you can be rich, make a start on that, right? That's what Judy said, that's what Judy wants. We use great content materials. So this is from Halliday University now, looking at ways to move fluids. So if you think about how we move fluids, he uses some simple electrodes. And do you do an electrode patterning step, Craig? Yeah. You do, right? So if you pattern an electrode, you can put an alternating electric field. You can actually drive fluids if those electrodes are different sizes. That's a really simple way of moving fluids around. We can exploit some other really fundamental phenomena. So this is paper fluidics, where we exploit the surface tension forces of the paper with raw liquid fluid. Now everybody here has probably done a paper chromatography experiment where you sort of put a drop of pen on and you put it in dissolved in cold chromatography. We've got not anything more fancy than that. But what we are doing is we're controlling the way the fluid moves, and we're putting different chemical and biological components in different parts of the paper. So we can do wonderful things like make COVID-19 diagnostics that save the world. It didn't really save the world, but everybody knows about a rapid antigen test. That is essentially a paper fluidic for us. Right, so really simple concepts can be really powerful and let us do important things to change the way we do. There's another way that we can detect things. This is one of my favourite examples, and this is published in a very good journal. And the first bit of this is something to do with Harry Potter. This is the Chamber of Secrets, where the book actually writes. Well, he goes, do you have my blood type? The answer is yes, A+, A positive. That ability to be able to read the answer from your questions is really a simple thing by using your eyes. Right, so this is not particularly challenging science, but it's particularly clever thinking, in that it's an intuitively simple step to read the answer to the question you want to know. Is my drinking water contaminated with E. coli? Yes or no? No, you don't care about it. It's yes, you might want to get to the hospital pretty quickly. The other detector element that we have nowadays is So the other unique thing about microfluidics is that as we scale down, we get some unique phenomena. I need to start the timer. Damn, you'll just have to keep your heart rate. One of the unique things when we scale the fluids down is we get what's called laminar flow. Now, I don't know whether you've been seeing this video, but the ratio between the yellow, the orange, and the blue fluid streams changes based on their flow rates. So if we have the yellow on really high, we get more yellow there. That don't mix. This is what's called laminar flow, and it's really useful because we can do a whole heap of wonderful things because of the physics says that don't mix. Craig has been using this many years ago now to look at mineral processing, extracting metals from mineral ores, and not just doing one, but doing hundreds to thousands of these to try and get up to industry scale processing. My favourite example, though, is not Craig. It's good, but it's the sperm sorting chip. Right, so this is a device that uses that laminar flow. We flow in sperm at the top left there. If I go back and see the video again. And the really high mobility sperms swim out of that laminar flow stream into the deep one down the bottom, and then you collect them. And you know they're good because they swam out to the other ones that are not so good. So you collect sperm based on how active they are, and that's just what you want to do in IVF. So I first heard about this in about 2007, and at that stage they just had their first baby being produced by this, and now this is one of the most common ways to select sperm for IVF. Very simple device. Also using that laminar flow device, we can start and think about creating artificial organs. So this is an artificial stream. And we use those two fluids and we move particles from one to the other. And on the particles we have some antibodies, some affinity to a pathogen, for example. And so we put that into the blood. We then use a magnetic field to separate those particles out into a thing, and then we put the blood back into it. Presto, you're miraculously healed. This was actually developed by DARPA in the US, so for the defense, the treatment of soldiers, and had some ridiculous amount of funding that actually tried to get it to work. And it does work. But we're now going beyond the spleen. So we're now looking at what else can we do with biology. What other parts of the body can we make? Can we make a lung? Can we make a heart? Can we make a kidney? And what's even more important, because we're making microfluidics, we connect it together. So can we make an artificial person that has all of the essential organs of a person, in which we might be able to do some pharmaceuticals of perhaps use? So can we collect those stem cells? Can we differentiate organ cells? Can we put them into little microfluidic devices? Can we then see what kind of drugs you might be susceptible to treat a particular drugs, to treat a particular disease that we've managed to initiate in that little microfluidic version of you? When I was a kid, this would be science fiction. This is almost science reality. We're not quite there yet, but we're really, really, really close. Justin Cooper-White in Queensland has been looking at some of this, and particularly taking stem cells, and looking at how the stem cells differentiate down through the microfluidic device, and what a particular generation of stem cell does to the next generation of cells, and how they then develop into different organ cells, and the little microenvironments and chemistry that these important cells. Judy at UTAS has been looking at cells in a different way, and he's been looking at circulating tumour cells for diagnostics. So when you have a cancer, we have surgery to remove the cancer. We try and get as much of it as possible, but it's also possible in that surgery process that some of the cells have been released and they get into your bloodstream and they circulate around the body and metastasize. He's developed a microfluidic device based on the physics in that particular geometry you can see there that will actually remove all the circulating tumour cells from your blood in about 2 or 3 hours. And so this is kind of like a dialysis machine. You have your surgery, you connect it up to this, and then hopefully you remove all of those cells that were disrupted in the surgery. Your blood goes back into you, and then hopefully you have a better recovery. Again, this is being commercialised out of Singapore over here. Also, David Inglis at Macquarie University has been looking at different ways to separate particles, and so that's similar to the cells, and again, similar types of things that you can do to what Majid was doing with cells and different types of particles, but in a different way. And combining these different, essentially physical shapes and designs, you can do a whole heap of really interesting phenomena to achieve something that you might want to achieve. Now, I don't know what you want to achieve. You don't know what you want to achieve yet. But there's a whole heap of ways you can do that with microfluidics. chemist, you can do chemistry too. So we can take molecules and we can react them together. This is not particularly exciting. It's making an orange dye. But one of the really interesting places where this has taken off is in radio isotopes for imaging, because they have a very short half-life, and so if you actually label those molecules at the bedside and then make them in a microwave device at the bedside, you get a high proportion of radioactive so you can imaging. And that's been commercialised out of the UK. We can also do chemistry in beakers, and these beakers are nanoliter in size. So think about your 1 litre bottle of Coke. Divide that by 1,000, you get a milliliter. Divide that by 1,000, you get a microliter. Divide that by 1,000, you get a nanoliter. These little green and red droplets here are nanoliter size. So we do chemistry on really small volumes now, which is really interesting because the kinetics of that reaction become quite efficient at low volumes. We can collect droplets and we can split droplets. This is all defined by the physics, not the chemistry. Right? So the physics of the shape of the droplets determines what we have. We can capture droplets. And we can make thousands and thousands of droplets a second, all doing maybe the same reaction, or even more interestingly, all doing slightly different reactions. And then being able to look at how that changes in each particular droplet. One of the really nice uses of single droplets is in STR profiling for forensics. So when you have a rape case, you're looking for male sperm in a large selection of female cells. And so if you just stick it all together and try and analyze it, you get a really large signal from the female cells. So if you actually enrich those cells in their own droplet and do the reaction, you actually get the perfect chemistry and perfect response from lots and lots of female cells, maybe 1 or 2 male cells. And because the male cells apply their own in their little droplet, you can actually find it really easily. And that means that you can process rape cases much more quicker than you have been previously. And this is a very interesting technology that has also been commercialised in the US. If you only want 1 drop, you can do that on demand, and Adrian Neal at Monash University is doing that using acoustic waves. So again, some electrodes and some voltages to dispense fluid on demand. And then Leslie Yeo at RMIT is going to be looking at how to use acoustics to make a fluid move in different ways to do interesting things. And this is some work where it's just making some of the microcentrifuges to be able to separate out some particles from Now from Griffith University has been doing some liquid droplet studies, been doing what's called liquid marbles. And so this liquid with particles on the outside, and because there's particles on the outside, they're quite stable. And that means you can do some really interesting things with those as well. Again, all of the chemistry is defined, and in this particular case, if you actually put some of the chemistry on the particles, you can then not only have these particles protected, you can do some very interesting reactions on the inside. To make all of these, you could go anywhere else, or you could just stay in Adelaide. So you've heard already that ANFF is a great place in Australia, but a lot of the things that I've shown you here can be made right here in the lab. And in fact, you will learn how to pretty much make any of those things over the next couple of days. Nothing I've shown you here is particularly fancy, but it requires a level of infrastructure and a level of capability that is really excellent in this particular place. So please take advantage of it. When you've figured out what you want to do, when you figure out how to do it, and when you've made it here, then you can go into Melbourne, where there is Shop Minfab, and they are one of the largest commercial microfluidic manufacturers in the world. They were developed in Melbourne, and so you've got the idea, ANFF has got the capability to prove your idea, and Minfab Shop in Melbourne has got the capability to take your idea, take your prototype, and bring it to the world. So this is really a wonderful place to be in. I'm a bit sad I'm not young again, but I'm also pretty happy I'm not young again. I'm old enough that, yeah, let's not go into that. So with that, I'm going to finish there, and I will wait and see if there's any questions. And if not, I've got some things that we might be interested in, you might be able to choose one, and I'll let the chair decide. Right, Craig says we have time for one vote. Who would like to see, I'm not going to ask, I'm just going to show my favourite one. Sorry, I'm just going to get rid of them next year. Assuming I come back next year. Oh, hang on. It's got to be the robots, right? That's it. Questions if you have any.
Thank you, Michael. I'm sure there'll be some questions. Any questions? Yes.
Oh, there.
Hello.
Good morning.
For a nice talk. I would like to ask, what industry are also interested in biology? Obviously, medicine, but maybe someone else.
So define interested. So what do you mean by what industry is interested in?
Okay, what industry wants to buy the lab?
What industry wants to buy lab on a chip? Lots of industries want to buy lab on a chip. So the defence industry is the first one that want to buy defence. But they want to buy everything. Right? That's a no-brainer. Pharma are particularly interested. So medical diagnostics are huge. Where else would you say, Craig? Environmental. Right, so if you can get low-cost analytical devices, you can start to do large-scale environmental sensing that takes scale without that. There's a huge shift to wearables. So if you've got an Apple Watch or a smartphone, it monitors your heart rate. There's a whole interest now in developing technology to not just measure your physical status, but your chemistry and what the industry is. So there's some of the emerging things. Where are some of the existing markets?
I was going to say drug detection, roadside drug detection, these sorts of techniques to be able to get a file quickly. The one Michael hasn't mentioned is not just sensing, but processing, so the manufacturing of specialty components, small spheres, threads, all sorts of different materials. Talked about a dye that was shown. So actual manufacturing using the microfluidic processes, so pharmaceutical industry, a range of manufacturers.
Lots. But they probably don't even know they want it there until you make it for.
Yeah, that's true.
This question here.
Look, two questions.
Very grateful, thank you. Things, but just so kind of a side thing. You mentioned your human on a chip.
Yeah.
All the different amazing ways in which you artificially recreate these things. I was wondering if you looked much into like artificial nose technologies. Because you mentioned with the biopsies, I guess that's like
So me personally, no.
yeah.
But there's a lot of people that have. I also know of a research project, I think it's out of QUT, that is looking to actually scan and replicate the 3D nasal cavity.
Yeah.
terms of the nose, yes, lots of people are looking at different receptors and how to put them in and where to put them in to create some biosensors.
And then the other one, Mitch, at the start with your microfluidic devices, that was the one that took 15,000 or 1,500
Layers.
Yeah. Was that, how is that done? Is that
So that was done with a 3D printer.
Yeah.
Yep. That was our first 3D printer.
Okay.
And you know, once we got our 3D printer, we printed the Eiffel Tower like everybody does, and then we made some fluidic devices. And that spiral design was one of the first ones we made because you can't make that easily by any other approach. And we were trying to highlight the advantages of 3D printing and not the disadvantages of 3D printing.
Okay. And is that with
No, that was with an acrylator hot and cold. So not here.
I'm just going back to that slide where you had that, how you had that like sort of chain going from the idea to that, that shot you have.
Yep.
Can you go into more detail about like a real example of a product that's gone through that?
Can I give an example? I'm the wrong person, but what's
I missed the question, sorry.
what's the eye chip from Minifab?
Oh, that's a good example. Yeah, it's called TLAB.
TLAB, right. So that's a really simple device that is just designed to collect a very small amount of fluid from the eye tear ducts. And I think it just does maybe a salinity measurement.
Yeah, it's got electrodes in the filter. The thing about the TLAB is you say it's a very simple device. The precision that you need to make it a very simple device to work is incredible. And the sort of microtechnologies you see this week will be the only way you can achieve a device like that.
That's right. So when I say simple device, the design is really simple. As Craig indicated, the manufacturing fidelity and the precision with which you need to manufacture was really, even now, is probably still pushing the capabilities of a lot of manufacturers because they make big stuff. Small stuff is really hard, particularly when you're making something maybe 10 microns with a 0.1 or 0.2 micron tolerance. And that's making still hard.
I guess one aspect that I'd say is it's not just the shape and the size of the components, it's also the surface wettability, materials and compatibility that become important, especially for a medical device. So the complexity in such a, it's essentially a piece of plastic with some electrodes in it that can be plugged into the machine. But the complexity has already happened upstream to deliver that, the right shape, material, surface wettability, all the things you need right up in that tiny channel.
So the other example I know that is made in Melbourne and shot is the Mitra, which is a blood spot device. And so the microfluidic device takes 4 10 microliter volumes of blood and it transfers those 10 microliters to a piece of paper to make a dry blood spot. And the reason that that's really interesting is because the microfluidics define the volume of blood to collect, irrespective of other blood parameters such as hematocrit, which changes how it deposits on blood if you do it other ways. So that was designed in Switzerland, but is manufactured in Melbourne. Yeah, making sure I'm not making that head. Yeah.
In terms of the actual physics behind like when the flow rate changes and they don't like why is that?
Sorry, why?
When you've got like the flow rate changes but they don't actually like why is that?
Oh, why is that? My simple chemistry, maybe Craig can give you a better example. My simple answer is that you've got a hole and you're just trying to force maybe 10 times more fluid of this one down, and so it just pushes the other one over because you have to have a conservation of mass moving out. And so it just redistributes its relative force to occupy the space that it's got. So if I make this one really high, these ones have to go a little bit thinner because this one's now higher.
So Mike, I think the question is also why don't they mix?
Yeah, why don't they?
Oh, why don't they mix? Why don't they mix?
Physics.
Laminar flow. I'm a chemist. So,
Because you sort of said physics, but like
the Mike was a chemist.
Yeah,
I'm a chemist, and I'll give it a shot. So we're talking about, so it's laminar flow. In this case, there's no turbulence in that system. The other thing is, so if you, when we talk about laminar flow, we talk about Reynolds numbers. In most of the devices that you see here, like the solvent extraction one that Michael showed from my own group, the Reynolds number might be 1 or 2. And you don't get turbulence until 2000 and above. And so these are incredibly laminar, if that's the thing. We have more laminar than laminar, but it's incredibly laminar. So far from mixing...
You're still not answering the question, Craig.
but that the timescale, it's a very fast flow. So the lateral diffusion is very slow compared to the lateral flow. And so they are mixing by diffusion, but they're not immiscible, so they're miscible. But you're not seeing it because you're looking at the very early timescales of that diffusion. Did I answer?
I don't know. Did you answer?
Michael doesn't open up. The question is happy.
Laminar, that's my chemist answer. It's laminar. Reynolds number is 100.
So, Michael, I might ask, we've about to go to the morning, so I might ask one more question. You went through all sorts of different capabilities, and just talked about the physics and the chemistry and everything else. Microfluidics, I think, is something incredibly multidisciplinary and needs a lot of collaboration. And so, this room's full of people from different fields and disciplines. So what's your advice to them about doing those types of multidisciplinary projects?
I guess I'm not quite sure of the question, Craig, but it's why not? So to me, it's not why. So to me, the question is understanding what you would like to learn, and then finding the people that you can work with to do that. And so I don't deal with physics. I'm a chemist. I can talk to physicists. I talk to engineers. I work with biologists. I don't have to know that because I've got them to know that. I know the chemistry, right? So I don't try and reinvent the wheel. I don't try and read every book, but I try and make sure that I can connect people who can help. So my advice is to try and figure out, and I know this is early, so right, you've probably got no idea what you want to do with your life yet. But find out what you're interested in, what really captivates your attention, and then network with the people who can help you realise that. And then you'll have lots of fun, and maybe get rich.
So, and maybe a good place to do that would be at a winter school. What do you think, Michael?
Oh, I don't know, Craig. There's some pretty dodgy people in particular from Tasmania. I don't know how they let them through the borders.
What Michael meant to say was this next 4 days is a great opportunity to network.
Oh, is that what I was supposed to say, Craig?
Including people like Michael. Let's thank Michael for his Thanks, Michael. So that brings us to the close of the first session. Morning tea will be in the foyer by the stairs, the other end of this building, so you don't have to go out the building if it's cold. I just saw it on my phone. Coldest morning Adelaide's had for, I don't know, some ridiculous amount of time, so stay inside and warm. We're going to come back at 10:45, so you've got about half an hour to meet and greet. The tour, Belle's got the tour sheets. If you haven't put your name down on the tour, especially if you're from interstate or overseas and you haven't jumped in there and written your name, do that straight away so we know who's doing what. And Belle hasn't told me this, but from previous years, I think this is when we're going to put you into your prac session groups as well, so there might be a bit of organisation there. So don't go you can go out there, but hang around at morning tea so that we can do any of the organisation that we need. Let's just thank all the speakers again. Okay, well done. You got back before I could get the technology working, so you're on time and I'm not. Great to hear all the chatter during the break. Well done getting into the groove of talking to people and meeting new people. Keep that up all week. You won't regret it, I promise you. We have some amazing sponsors. You might have noticed that we didn't charge you a cent to come along. There's a good reason for that. We've got great support through ANFF, but also some industry sponsors, and you will have seen also some tables. You will have seen some tables in the foyer during the morning tea. Can I just ask you to please go and talk to the people who have the tables set up and have brought gear to show you and lots of toys and got involved and also funded the school. Make them feel very welcome and make sure they know it's worthwhile for them to be amongst us, because their support really makes the world go round when it comes to winter school. In that perspective, we have a short video in between some of our sessions, which is just to acknowledge and give the sponsors a chance to tell a little bit about themselves. And so the first sponsor video I'm going to show is from, I think it's Nano Vacuum. Hopefully I've got that right. And here we go. Oh, hang on. Anyone read that? Which one do I do to get rid of the... I want to shrink it. Hide. Is it that one? No. Hide video panel. Okay.
I think I want to hide this as well. Let's just do it anyway. So a big thank you to Nano Vacuum. Please see their stall. The other thing that we're very grateful for is the dinner tonight. If you don't already know, 5:30 here in the same building that you're in. Nano Vacuum has sponsored our winter school dinner, opening dinner. So be here then, have a great time, get to know more people and make the most of the opportunity to connect. Whoops, I'm playing it again. Let me see if I can quickly switch out. Sorry, we've lost the local screen, so we're doing things with our squinty eyes to try and see. I'm getting old, like Michael was saying. And I think we're up to...
Sorry.
It's...
On the other screen.
Oh.
And the top one, yeah.
Okay. Yeah. So my glasses are good, but not that good. So we're going to just break out to share. And I'll try again. Okay. Excellent. So it's my absolute pleasure to introduce to you Professor Paul Weber, all the way to South Australia from Utah Valley University in the US. Paul is a faculty member and researcher in thin film physics and nanotechnology pedagogy at the UVU, as I said. He spearheaded a $704,000 National Science Foundation grant project to create virtual reality simulations used as pre-training for laboratory exercises. As a visiting scholar to the Future Industries Institute, he'll be continuing to develop his interests in creating new technology and teaching methods for nanotechnology processes and fostering effective industry-academia partnerships. And Paul has been here for a few weeks and is on sabbatical for a year, so we're looking forward to being very productive to have his expertise here. He also runs a school similar to this with slightly different emphasis in the US, and so we got to know each other through that, and we have a passion for the types of events that we're dealing with today. So please make Paul feel absolutely warmly welcomed.
Thank you. Thank you.
Where do you want to be?
Now the microphone. I just want to make sure that the microphone is on.
Okay.
Great.
Just give me a sec.
Oh,
That's on full volume, so you'll be fine.
okay.
Yeah.
And this is working.
Is it working? Yeah.
Yes. All right, good morning, everyone. It's my pleasure to offer this first pedagogical talk, which is on thin film coatings, kind of the foundation for so much of the processes and the devices and the work that is done here. So I'm at Utah Valley University. It's in about the center of the state of Utah. And so it's my absolute pleasure to be here and to be able to speak to you, to give you a survey of the methods of producing thin film coatings. Now, I have a very American accent, and I can't apologize for that. If there are any words that I use that are peculiar and odd, I hope you will feel free to interrupt me and say, "What did you say?" So please. So please advance.
I just need to do one click. Now try. Oh,
there we go. You know, I just want to say that we live in a thin film coating ourselves, and it's a most beautiful thing to see the blue surface of the earth and the thin veneer in which all life on this planet occurs. So thin film coatings, a lot of interesting applications. I'll be touching on some optical applications, protective coatings, very important. But perhaps the ultimate, maybe why most of you are here today, is because of the patterned coatings that are used to produce chips, to produce semiconductor devices. Very important. They're all involved with this process of how do you coat a very thin layer of material onto a substrate. I'll just mention that my background started in quite a different area, and it went off into a different field when, at my local university, the department chair said, "We have an old sputtering machine here that no one has ever been able to operate. Can you make it work?" And so I did, and got some students involved with projects on it, and that's why I'm here. Okay, I'm going to cover this topic in the traditional form of two basic types of thin film vapor deposition: physical vapor deposition and chemical vapor deposition. So I'm a physicist, so I look at things from a physics point of view. And that can be very advantageous in many of these processes because the physics is very important. Under the physical vapor deposition processes, which are direct transfer of a material from from a target or source material onto a substrate, there are the topics of sputter deposition, thermal vapor deposition, the two most important ones, and I'll also mention the other ones that use electrons and ions in order to assist with the deposition process, and lasers. Chemical vapor deposition, perhaps one of the most commonly used in industry at least. Chemical vapor deposition processes, and also the enhancements that are used in this methodology, such as plasma enhancement and microwave enhanced chemical vapor deposition. And then I'll touch on atomic layer deposition, really the key to being able to go to the ultimate in miniaturizing circuits and hopefully keeping up with Moore's law. So first things first, we need a good vacuum. So there's a traditional demarcation or division of vacuum levels into several categories. Rough vacuum and high vacuum are below atmospheric pressure. Here, what I want to mention, the vacuum, of course, is supremely important because if there's material in the way, any kind of residual oxygen or atmosphere between where the transfer of material is happening, then it won't work. So we demarcate rough vacuum to be roughly 1/1,000,000th of the level of atmospheric pressure. I know, I have these units of torr. Don't worry about those. That's 1/1,000,000th for a rough vacuum. So what's important in understanding the effect of vacuum is this idea of mean free path. How far do molecules move before they run into something else? And in this room right now, the air that we're breathing, that's 70 nanometers. And I'll show you how much that is. It's that much. I'm being facetious. It's too small to visualize. Now, if you go down to 1,000,000th, you'll have roughly a 1/1,000,000th of atmospheric pressure, 5 centimeter vacuum length. That's called the rough vacuum, that level. And very high vacuum is at 1,000 times more lower vacuum than that. And the mean free path, then the distance that molecules will transfer, is about 50 meters before they run into something else. That divides the class of vacuum pumps into two categories. Those are called roughing pumps, and those are called high vacuum pumps. They operate on different physical principles because the environment that they're pumping on is fundamentally different. So imagine in this room, if we were to pack right now 1,000 people into this room. I think we could do it. I think they'd be shoulder to shoulder. But as they try to move around, they'll bump into someone else before they run into a wall or before they go out of a door. If you now pump out a lot of those people, and so that you have, say, 10 people in here instead of 1,000, and let them walk around, they'll probably run into the walls or go out the door before they'll run into someone else. And that is the difference in the physics of why the pumping mechanisms are different between a rough vacuum and a high vacuum. So the types of pumps which are used in order to achieve this are fundamentally different. The rough pumps are typically rotary vane vacuum pumps, which have an ingenious spring-loaded mechanism that will spin around and will chase any molecules coming in out the other end. It can go down to the rough vacuum level, which is about 1/1,000,000th of atmospheric pressure. But beyond that, then you have to switch to a different mode. And the most common one, perhaps, for the high vacuum purposes is the turbomolecular pump, which looks very much like a jet engine and works in very much the same principle, exhausting gases by high-speed rotation of the blades that you see there. Okay, so you'll see a lot of those kinds of pumps here at the Institute. So let's cover the first topic, one of the simplest ones, thin film deposition by evaporation. So with the high vacuum that's created, now this laser, let's see. Unfortunate thing about the laser is then it only will highlight one screen. So the chamber that you see there, where the evaporation is happening, there's a crucible at the very bottom that has the source material. And it's literally turned into molten form by high temperature, but it's inside of a vacuum, so it can actually boil. And molecules and atoms will come from the surface by simple evaporation process. That's important because the speeds with which those atoms or molecules are emitted are thermal velocities in the range of perhaps a few hundred meters per second. That's how fast they're moving. That's still quite fast. So the molecules or atoms are emitted, in this case, in the upward direction. They'll simply strike the layer that the substrate that you're trying to coat, and they'll stay stuck there. So you can imagine if they run into a surface at hundreds of meters per second, there's a good chance they'll embed, and you can create coatings by this simple method. It has its limitations because you need to melt whatever it is that's in the crucible in order to get it to transfer from the lower to the upper. So tungsten, as an example, because those boats, those crucibles that hold the material that you're melting, they're made of tungsten. So how are you going to melt tungsten inside of a tungsten crucible? But nonetheless, it's a very common method still in use. Thin film deposition by sputtering, perhaps one of the most important ones for physical vapor deposition. So this is a ballistic transfer of material where you simply take material that you want to transfer into a thin layer onto a substrate, and you bombard it with something. So you're dislodging atoms or molecules at a time, individual ones, lots of them, however, and they're flying off across space because they've received momentum transfer from whatever medium that you're using to do the sputtering, and again, they embed on the sample that you're trying to coat onto the substrate. There are three different media that I've mentioned here that accomplish that. Accelerated ions of a gas, in particular argon. So if you apply an RF field, or apply an electric field rather, between the substrate and the target, you can cause ionization to happen, and you've got this argon atom that has perhaps lost an electron, and it's moving, and it pounds into the target and liberates some atoms or molecules. You can sputter coat elements as well as ceramic materials, glasses, all sorts of things by this simple process of running something into the target and dislodging atoms and molecules, and they'll fly off of the surface. Now, the way that they fly off the surface is very important. They're going at higher speeds. So typically in the few thousands of meters per second. Therefore, the speed with which they hit the substrate is higher, and you have potentially a firmer coating as a result of that because of the higher speeds with which the material atoms or molecules hit that substrate surface. Excuse me. So there are important factors then that will determine the quality of the layer that's sputter-coated onto a given surface. So here's a simple model called the zone structure model, which tells you how they settle onto the substrate that you're coating. So as you build these up by running more and more argon ions, for example, to transfer more material from the target to the substrate, it depends on these parameters, the pressure of argon in the chamber, and also because there is a small amount of argon. You have to have the argon there in order to, in this case at least, for argon transfer, you have to have it there in order to transfer the atoms or molecules. So it tends to be that the lower pressure of argon that you have in the chamber, the better, the more dense the deposition is. You can perhaps think of that as there are less other argon atoms to interfere with each other, and therefore you have a better transfer of material from target to substrate. The other important factor is, and this is almost always done, is to moderate the temperature of the substrate. So between those two factors, there's this model which says if you want a denser coating, then run at a lower argon pressure and also increase the pressure, the temperature rather, of the substrate. These are dramatic examples and I got these from Professor Colin Hall here at the Future Industries Institute. That shows the difference in structure. You can see there are almost hair-like layers for the low-density deposition. If you move along that plot there towards increased temperature, decreased pressure, then you'll have a medium layer. It kind of reminds me a little bit of carpeting in a house. But it's the way that they form as a result of the sputter deposition. And then you can ultimately, of course, produce a high-density layer where you don't see any of this substructure that's happening. You have about the most dense packing of atoms and molecules that's possible for the layer that you have deposited. I want to mention how they monitor how thick the film is. Very important. You want to produce a 100 nanometer thick film. How do you know how thick the film is that you're depositing? And this is the way that they do it. It's a quartz thickness monitor, a crystal thickness monitor. That's inside the chamber. So if you measure the frequency at the beginning of your sputter deposition process, and then monitor that frequency as the deposition occurs, the frequency will change. It will decrease because it's also being coated by material that's being sputtered inside the chamber. So using that, you can have a gauge of how thick your layer is, when to stop the sputter deposition process because you've got the thickness that you wanted. Okay, those are the physical vapor deposition processes. I want to touch on now the chemical vapor deposition processes. So they operate in a completely different way. They have, of course, start with a good vacuum as well, but then you introduce gases that can react chemically inside the chamber. That's the key thing. Physical vapor deposition, no chemical interaction. But chemical vapor deposition, that's how it works. And in particular, you can produce polymers this way by injecting monomers, even combinations of monomers, into a rarefied form into the chamber, and then have them react and coat the surface. You see, it's quite different because it's like a gas is developing that's not moving at hundreds or thousands of meters per second. It's simply a gas that's static, but not static, but with very low circulation inside of the chamber. Therefore, the nature of the coating is quite different from what you get from the physical vapor deposition processes. Many of the most important applications here, most at least common applications for chemical vapor deposition, they're so prolific around us that we don't even know that they're there. These pieces of potatoes, which I think are called crisps here, not chips, but crisp chips, or anyway. The potato crisps are inside of a bag that preserves the freshness of the chips by having a layer coating, very thin layer coating of metal, in order to make sure that light doesn't degrade the chips and so on, so that they stay fresher for longer. This is a very common use of this technique. But if you go to the hardware store and get a drill bit that looks like it has a gold color to it, that has also been produced by this process of chemical vapor deposition, because it has a thin coating of titanium nitride on it. That's produced by CVD. And there's a knife that has titanium carbon nitride, which is also very hard coating. These are very hard ceramic coatings that are resistant to wear, and you'll see them also in the mining industry, for example, where they need to have very hard cutting surfaces. These processes are interesting. You know, if you come into the building here, you'll see very impressive placards that say you're about to enter a building where you've got some potentially nasty chemicals, okay? And yes, they are used for CVD. So some of those there are extremely dangerous: phosgene, arsine, silane. I've heard stories about what happens. Silane will burst into flames spontaneously when exposed to the air. So that's on top of its poisonous properties anyway. But they're just the thing that you need to have in order to do these kinds of chemical vapor deposition. You can enhance the process then by using plasmas and microwaves as well. And also, you can, as with physical vapor deposition, you can also influence the quality of the coating by the temperature that you apply to the substrate. So all you've done in addition to the chemicals is you added this plasma, which can speed up, it can enhance the rate of deposition, or microwave enhancement as well. So on the right-hand side, this is showing, you can see that the substrate holder on the bottom, it's glowing red because it's quite hot. The plasma is the purple region, the gaseous region on the top. They're growing carbon nanotubes in this way by using chemical vapor deposition. So again, I want to emphasize the difference in the type of physics. CVD, I think of it more as an enveloping wafer, a vapor rather, that's filling the chamber and coating everything that it settles upon. But PVD is more of a ballistic process where you're shooting molecules or atoms at the substrate that you're wanting to coat. This makes a big difference because then if you have features on the surface of the substrate, the ones that have a direct line of sight exposure to in physical vapor deposition, those will be coated very well. But if you have a vertical wall that is in the same direction as the molecules or atoms are traveling, it won't receive much coating. And that makes a big difference for one of the most important applications. If you want to build semiconductor devices, the liftoff process. In the liftoff process, you start with photoresist that transfers a pattern onto a substrate. Transfers that pattern, and then at this middle stage right here, you can see that one. After you've done the developer, you have a photoresist that's on top of the substrate. But what you really want is metal that's on the substrate. So what's done after that is to sputter coat metal onto the photoresist pattern. But here's the key thing. You want to make sure that in the subsequent washing off of the photoresist that you don't coat those edges that are next to the material that you want to have stay. Because then you can apply a washing solution to remove the photoresist that's remaining together with the metal that's on top of it. Wash that away. It's called a sacrificial layer. And then you'll have just that metal, which is now rather firmly bonded onto the wafer that you're producing. Okay? Very simple process. Repeat this process and other etching processes and so on about 1,000 times, and you'll have a typical computer chip. All right. The last process now that I want to touch upon is atomic layer deposition. Very important. This is getting now down to the point where they're controlling deposition at the atomic layer across a substrate. So with the correct combination of chemicals, there are many variants of this, many different combinations of chemicals that you can produce to give a given coating. In this case, it's aluminum oxide. So you'll see that a surface is first prepared with an activating process. In this case, there are hydroxyl radicals that are with the oxygens attached to the surface, exposing the hydrogen atoms. Then you can introduce a compound, in this case, trimethyl aluminum. It's an aluminum atom with 3 methyl radicals attached. And they will attach, but only at those places where there's an exposed hydrogen at the surface. And therefore, it means that only one molecular layer will be deposited. Once a given site is taken, no more molecules will attach there. So you'll have a nice second layer, a molecular layer of material that's deposited by this chemical. Then next you can do a simple, in this case, water, exposure to water, and it will bond again, but only at those individual sites. So layer by layer, and then you can continue the process. Layer, next layer, and you can build up atomic layers of material. So this is very important in being able to scale down devices to the level, to ever smaller levels that are necessary in order to produce, for example, semiconductor chips. Quality control. So, clean rooms. Clean rooms, why are they important? Because a piece of dust, we're breathing them in all the time right now. Our lungs can handle that. They can expel the dust that we breathe in. Most of it's so small you can't see it. But if it gets onto a surface that you're patterning with the goal of producing some kind of computer chip, it can be disastrous because it looks more like a boulder or an asteroid hitting the surface. And you can wipe out an entire chip just because of having a piece of dust like that on the surface. So very important to have clean rooms in order to make sure that the quality of the coating is as high as possible. And you can improve the adhesion here, I've mentioned, by several different processes that you may see this coming week, including plasma cleaning, activation. A common trick that's also done is, it turns out that the element chromium is a good element that will help. It acts kind of like glue to make sure that if you're coating something else like gold onto glass, if you try to coat gold onto glass, and I've done it many times without the intermediate coating, I can take my fingernail and scratch off the gold. It doesn't stick. But do some plasma cleaning, and also apply that chromium layer, and it will stick very well. The strength of the adhesion is checked by some very complicated tests. No, it's not that complicated. A piece of tape. You simply take a piece of tape and pull on it and see if the coating sticks. There's also a scratch test, and that's illustrated here, and you can imagine what that is. But really, there are more methods that are a little bit more rigorous and quantitative for assessing the adhesion. So that leads me into the next topic of inspection and characterization. So electron microscopy is very important in this area in order to see the quality of the structures. Thickness of layers measured with profilometers. Here I've illustrated a stylus profilometer, very common, where a tiny needle drags across the surface and it can measure thicknesses of films down to few nanometer levels. Ellipsometry is very important for assessing the thickness of transparent layers. And I've mentioned resistive measurements and also hardness measurements. Here, the hardness measurement is a little bit better assessment of the quality. Use a nano indenter or a micro indenter to put a dent into the surface and to see how big is the divot that is left behind from this indentation process. And it's a measurement of how hard the coating is that you put down. Examples of thin film coatings. An anti-reflective coating, very valuable if you want to take pictures of people who are wearing glasses so you don't see a bunch of glare in the face. That's achieved by putting down a coating that's about a quarter wavelength of the average wavelength of visible light in order to extinguish the reflection. Here at Future Industries Institute, a number of different applications that you will see as you're here, and you should talk with these professors more to see about the work that they've done. So Professor Colin Hall here has done a great deal with producing polymer mirrors of very high hardness, and they're used now in Ford trucks, in F-150 trucks. Better than glass, because glass can scratch, whereas these are and glass breaks because it's so brittle. But these mirrors, no, they're much more resilient. Okay, and Dr. Camille Zuber here has worked with super hydrophobic coatings, among other things. These are coatings that will shed water just by having a coating of the material on top of it. Let me see if I can make this go. On the right-hand side, it's slow motion. And on the left-hand side, you can see this droplet in full speed. It's simply racing down the surface. It's beautiful. And at the top, they're trying to get a droplet of water at the end of the probe in order to wet the surface. It won't wet. It won't wet. Lotus leaves in nature, for example, have the same property of shedding water. Very important. If you want to produce a raincoat, for example, it would be quite useful. A rain jacket. All right, I'd like to finish with a couple of examples. These are things that we've looked at Utah Valley. The first one has to do with the same kind of coating that's used for an anti-reflection or anti-glare coating that you saw in the glasses the previous slide. Very simple process. You simply put a layer down enough so that the two rays of light, both the rays of light that are reflecting directly from the surface and those that have traveled through the layer and hit the reflecting surface and bounce back, you want those two to be out of phase and to cancel each other. So very, very easy idea physically. You see them all the time after a rainstorm, and you see oil on water surface, and you see this nice rainbow pattern because the thickness of the oil is not constant. It's getting thinner and thinner, therefore you reinforce different colors. The soap film on the right is a dramatic example. This is a soap film that's hanging in gravity. So because of that, the profile spreads out as you go down, and therefore you get the beautiful sequence of color rings that you have here. Well, in this project that we looked at what can you do with, in terms of producing a mirror that doesn't have any metal in it. We call it a dielectric mirror. So we started with a glass substrate and added subsequent coatings, alternating coatings of silicon dioxide and titanium dioxide. They have different indices of refraction. What can you make with that? So we thought, let's try to make a mirror that doesn't have any metal in it. Okay, very simple idea. Okay, thank you. Almost there. So in this case, we took alternating layers and we decided to build many of those. And there's a beautiful program called TF-Calc, which you can use to simulate optical coatings. And we use that in order, my student used that in order to design this mirror. So this is what he did. 19 layers alternating TiO2, SiO2. And you would think that if you just made subsequent layers all to be quarter wavelength, then you would get the best reflection. Yes, but perhaps for only one wavelength. What if you want good reflection over the entire visible spectrum? And so if you do many layers of just simple layers that are all the same thickness, you'll get a reasonable result. That's the bottom two curves. But what TF-Calc allows you to do is to run simulations of what happens if you let the layers change in thickness. Let them become slightly different. Can you get a better result over the entire visible spectrum? And what you can see here on the left-hand side, that top yellow curve, he was able to achieve greater than 95% reflectance over the entire visible spectrum. So you have a better quality mirror. These things are possible if you increase the number of layers. TF-Calc will let you go, it can do 100 layers. And this is just a fun gee whiz example that I'll close with. A contrasting example. What if you wanted to have no reflection happening? This is a material called Vanta Black that you might have heard of. The blackest material that people have created. So it works by absorbing all of the visible light that comes onto it. How does it do it? And the students that we had said, let's see how it works. They put it under an electron microscope. A beautiful idea, because the electron microscope doesn't use visible light. Therefore, you can see what's really happening. You can see these nodule growths here, which are made of a carbon-rich material that cause the light to scatter, and it doesn't come out. So and this is actually done with an optical microscope, but they had to run it for many minutes because Vanta black, absorbs almost all of the light. And you can see the size and structure, both in terms of the lateral dimensions, but also depth dimensions. It's a profilometer microscope. Okay, I'll conclude now. There are many important applications in nearly any direction that you look. And really, if you have any sort of cell phone, computer, they're everywhere. So the applications, perhaps the most important field, generally semiconductor chip manufacturing, of course. But new coatings can be developed, are being developed all the time. And I found the experience of working with a student to tweak the 19 layers of this multi-layer coating to be very instructional, because it says there are new things there still that you can discover, new coatings that can be produced. And of course here at this institute, they are of course champions in that. I hope you take advantage of all their expertise to learn as much from them as possible, and to learn the things that they have done already in terms of developing new coatings. Finally, I want to thank Craig and Belle. Belle is not here, but I thank them very much for their generous invitation to come and visit here, to visit Australia and also the Future Industries Institute. Thank you.
Thank you very much, Paul. A perfect explanation of thin film coatings. Are there any questions for Paul? We've got time for a quick one. Yes.
Maybe not respect, obviously, really beautiful. But just referring to this part of the position, if the sputter coating to the evaporation position, and in terms of stability and firmness, but I was just wondering in terms of directionality, like which one, if they could be compared quite easily.
Yes. So perhaps the thermal vapor deposition would be a little bit better in that regard, because you have a more confined beam coming from just where the crucible is.
Yeah.
Whereas if you use sputter deposition, you'll have a region over which the deposition, and you can have cross, yes.
Yeah, so I think the way you worded that is more positive, but I think I'm kind of interested in sputter coating because I don't have too much directionality.
Yes.
With some of my lift off.
Yes.
Yeah, anyway.
You can improve that to a certain level by having masks.
Yeah,
Yes.
definitely, yeah.
Yes.
And maybe, sorry, I'm using too much for the visual time.
No, please.
Yeah, I was just wondering about with the lift off. Photoresist as well with that. Like the same can be as long as that we deal with the thermal evaporation.
Yes, I'm sure it depends on the type of photoresist that's used. I can't speak to that directly because I don't have a lot of experience in that. But I know that the key thing is to be able to keep those shoulder areas. Yes. Very important. If you cover those, then some metal will be left behind, and of course you don't have a chip anymore. Yes. Sure.
Okay. Just while we wait, we'll do one more question, but I'll ask Sophia to come up so we can set up for the next presentation. But yes, another question over here behind.
Yes. You're welcome.
This might be for you and Professor Craig as well. Can we coat the inner channels of a microfluidic chip with thin film to reduce the surface effects?
Can we do that? That's a great question. The inner channels. Yeah, so the inner channels, I think, would be different. Certainly not by thermal vapor deposition or sputter deposition. But you might have to go to a different kind of technique. Perhaps something like electroplating would be an option. Electroplating, I didn't talk about that, but you can cause transfer of materials to coat surfaces just by having the right solutions of electrolytes. And I don't know if Craig has ever fielded that question before. Perhaps he wants to add something.
I think sorry, I was multitasking. I'm not very good at that. The question is, can you coat inside the microchannels? Yeah. What you can do, so if you can use a chemical approach, like in wet chemistry, that's ideal because you can flow through and get the effect you're looking for. But often what we'll do is have two halves. So if we can coat both and then do some bonding, you can trap that surface chemistry in the channel during the fabrication. And there's a really nice talk on Friday, I think it is, where we talk about packaging and the different bonding techniques. Bonding is incredibly challenging. It's the most underestimated step, and so make sure you pay good attention on Friday because that can be the secret to making that work or not. Okay, so we do have a gift for you, Paul. Let's thank Paul for a really wonderful talk.
Thank you. Thank you. Thank you very much.
Okay, I'll just grab the mic for a sec. So let me get rid of this. Is this the one? Yes. Okay, so I just make a quick note. You'll see that there's 8 different practicals. I can tell you, we'll do a quiz later, I can tell you that 7 of the practicals somehow have something to do with the talks you've already heard this morning. And you've only heard, 3 talks so far. So we're going to get your hands dirty on some of these things that you've seen here, whether it's thin film coatings, etching, etc. And one of those things is photolithography, which is the patterning step that enables you to actually turn what would normally be a homogeneous coating into something that's functional and has some structure. And so that's one example, or microfluidic channels, or whatever it might be. So Sophia is with us in the ANFF-SA. So the SA node of ANFF here, right here at Mawson Lakes. She's an expert on clean room techniques, including photolithography, but many other things too. And so one of those experts who you should come and tap on the shoulder and have a chat to later to pick her brains about what you might be able to do in your work. Sophia, thank you for being willing to talk to us today. And everyone, let's make her feel very welcome.
Thank you, Craig. And hi, everyone. I'm Sophia, so I'm here to talk about photolithography. So photolithography is a very important step in our microfabrication. So in this presentation, we will talk about the materials we use in the photolithography and the process and the following streams of process. So most of the word will come from the Greek. So photolithography in the Greek means the photo means the light or photolithographic. And the lithography means just the stone write. So basically, photolithography is we just use light to write something on our substrate. So let's have a quick look on how a chip is made. So you can see we have the sand. We use this sand to grow the crystal. After we grow this crystal, we will slice them into the wafers as a thin film. And then we're coating the photolithographic on the top. We use the mask to expose the pattern. After the inspection, we can deposit like sputtering, doing some metal on top. And after that, you can see it is not just one step of the photolithography. There are multiple steps, so you can create like computer chips, which you use in your phone or computer or any electronic devices. So you will create multiple chips on the wafer. After this, you will do an inspection and then dice it into individual chips and package them. Then you can use them into your electronic device. Okay, so let's talk about the elements in the photolithography. So I like to think this process is like a party. So for your party, you need a special room for this. And in photolithography process, we need a yellow room to accommodate our material, because the material we use in the photolithography is light sensitive, so we need to block out all the UV lights. It's just like your special room in your party. Then we need a substrate. So you can imagine when you are going to have a party, you need to serve some food in your party. Let's say we are going to serve the pizza. And this pizza paste is just like our substrate. It's the circle, round, big things. Let's just call it wafer or substrate. And often this will be the silicon substrate or glass or quartz substrate. After you have your pizza base, now you need to have your pizza sauce. And this pizza sauce is just like the photoresist in our photolithography. You will spread them onto your pizza base and then put them into an oven. So just the same, our photoresist will have two different types. We have two different types of photoresist. One is positive photoresist, one is negative photoresist. And the difference between them is one will dissolve in exposed area when developing, and the other one it will dissolve in unexposed area when developing. So you will use this photoresist based on your application. And the next is the mask. So let's say we have our pizza in our party, then we're going to serve some drinks and the cake or the desserts. So you will have like this sieve. This sieve will just change the pattern from the pattern from the sieve to your coffee or to your cake. Similarly, this is the mask. So this mask-based material will be glass, and we will have a chromium coating on the top, and then we create a pattern. So this pattern, we can transfer this onto our substrate. Okay. So after that, we have our food, our drinks, our cake, but you need to face the reality. In your party, you need to come to an end, and if it is the end of the party, you create a lot of mess. Now you want to clean it up. So developer is just like the cleaning product for our party. It can wash away anything you don't want. So you can see from all this flow chart. For the positive photoresist, the developer will wash away the exposed part. And for the negative photoresist, it will wash away the unexposed part. Okay, now we have all the elements for our party, for our photolithography process. Let's talk about how do we do this photolithography. First is the substrate cleaning and the preparation. Next, we are going to apply our photoresist and do the soft bake. Next, we will do the exposure, or if you need the post-exposure bake if needed. And then we do the development and then visual inspection. After this is basically the photolithography process. Now we can do some downstream process. Let's start from the beginning. In the beginning, we need to clean the substrate. So there are multiple ways we can clean up substrate. First, when you get a substrate, you might get a moisture or water on the surface. So we can use dehydration bag to remove all this moisture. This is often done by a hot plate or put them in the oven. all your substrate will have particles or other materials on the top. You want it be as clean as possible. You can use solvent, oxygen plasma, or piranha solution to clean it out. So this is what happens if you don't clean your substrate. You will have some defect on the top. After you coating the photoresist, when you see this defect, you will want to redo it again. And after the cleaning, sometimes we need an adhesion layer to adhere our substrate and the photoresist. It's just like a glue. So in order to increase the adhesion, sometimes it's a material called HMDS. We will apply them onto our wafer. So this is what happens when you don't use HMDS. You can see there are no pattern, almost no pattern on the top of your substrate. And the other one with HMDS, you can see the photoresist is stick very well on the substrate. After you coating your photoresist, after you prepare your surface, it's very clean and you have an adhesion layer. Now the next step is to coating the photoresist. So there are two ways in our lab to coating the photoresist. The first way is to use the spin coater. So we just apply the photoresist on the top of the wafer and then spin it up. So you can see from this animation, we apply the photoresist on the top of the substrate. First, we use the lower speed just to spread the photoresist on the whole wafer. And then we will increase the speed just to uniformly coating the photoresist and then create a thin film of the photoresist. The next one is spray coating. Because you are not just only do photolithographic once, you might do different multiple times. Then your surface will become not even, or you will have higher aspect ratios pattern. Now you can use spray coating. It usually uses the nozzle to spread the photoresist from right to left, and it will move up and down just to create a even surface onto your substrate. So this is like we use the nozzle to spread the photoresist. After you coating the photoresist, you can do a visual inspection just to see is there any defect in your coating. Sometimes you will have air bubbles if you don't remove the moisture or the water on the surface, and you will have this comic or flares because there are particles on your substrate you didn't clean well. Or you have some uncoating area, it's just you apply 2 layers of the photoresist or pinholes. Yeah, there are so many things can go wrong, but if you have uneven and a perfect photoresist coating, you can move on to the next step. After the coating photoresist, we can do the exposure now. So there are different ways to do the exposure. One way is to use mask. The other way just don't use the mask. The first one, we use the mask photolithographic. This is our mask aligner in the clean room. Let's have a look how the mask aligner works. So you will have a patterned mask, and then you shine a light onto the top. It will transfer the pattern onto your substrate. And the other one, you just remove the mask and you don't want to use it anymore. You can use the direct light photolithographic. This direct light photolithographic is just to use the laser or to use E-beam photolithographic to expose the pattern from one dot to another dot and then to create a pattern. So let's have a look. This is the electron beam photolithographic, but it's similar to all the masks as the photolithographic. You can see it just exposed one dot by dot and then to create a pattern. And because the technology is developing, we not just only expose one dot at a time. We can expose the one stripe, and it will be It will be quicker when we do the maskless photolithography. After exposure, you can also do some QA inspection. There are some possible defects in the exposure. There's overexposure if you use the too much light, and underexposure if the light is not enough. How do I say it? Sorry. So overexposure, if your light dose is too high, you will create an overexposure pattern. If the dose is too low, you will cause underexposure pattern. And just like we say, we have different layers of the photolithographic, and you will use this alignment mark to align your pattern. If the alignment is not correct, you will create this misalignment pattern. Once you have this misalignment pattern, there is no way to keep going. The best way is just to wash away all this photoresist and then do this again. After the exposure, we will do the development, and then we will do a simple visual inspection. So after the resist has been exposed, you will go to the development to selectively remove the part you don't want. And the developer is kind of a chemical solution. It will wash away the photoresist you don't want. So it's just like this old camera film. I have never done this. So it will just develop these pictures in a dark room, and then sometimes you will just reveal what's in the photo. And it's the same thing, we just put our substrate into the developer, and then just to gently shake it, and then it will wash away all the photoresist we don't want. And after development, there's something will go wrong in here. If the development time is too short, you will get an incomplete development. And then you will have some photoresist still on the bottom of your substrate. And just like the professor said, when you are going to do some sputtering, if there are photoresist on the bottom of your substrate, when you remove these photoresist, your pattern will just all wash away. And this is incomplete development. And the other one is under development. If you put this substrate into your developer for far too long, your pattern will become bigger or maybe different from your design. The under development is also you didn't develop it very completely. The over development is that you will create a big pattern or the different from your design. Okay, so after your development and the inspection is complete, you will finish your photolithography process. Now you can start going to do your downstream process. The following process, there are multiple steps. There are multiple processes we can do. We have ion implantation, wet etching, molding. Plasma etching is also dry etching, electroplating, and the leaf-off process. You will use some of them in your practicals. Yep. The first is wet and dry etching. So etching is a process used to remove the surface layer from the material. So the wet etching, you can see from the words, we just use wet chemical to etch the pattern to etch the material. And this will to etch the material. Yeah. The dry etching is to use gas or plasma to etch the material. You can see the profile is very different. And then you need to select one of them based on your application. And the next one is leaf-off. Leaf-off is done by performing photolithography on your wafer before coating your material. So I'll just give you a quick process. So the first, you will apply the photoresist on your substrate, and then you pattern it. Now you start coating or sputtering your material on top of the photoresist and the wafer. And then you will put this wafer in the solvent, like most of the time it will be acetone. So you will remove the photoresist part. Then you will leave your material on top of your substrate. The next is PDMF soft lithographic. So this will create like a mold. We will create the mold, and then we will apply the PDMS on top of the mold, cure them in under 65 degrees. Then we can transfer the pattern from the mold to the PDMS pattern, to a PDMS. So now this will be one of our practicals. So welcome to join us to have a look. So let's just have a quick recap of this photolithography process.
The building up process begins. Just as you draw blueprints to build a building, you draw a circuit design onto a wafer, which is called the photolithography process. It is called photo for short because it is similar to developing a photo taken on a film camera. With semiconductors, a photomask functions as the film. A photomask is a glass substrate with a computer-designed circuit pattern. In order to draw the circuit on the wafer, the photoresist, a material that responds to light, is applied thinly and evenly on the oxide film previously placed on the wafer. Now, when light transfers the patterned photomask, the circuit is drawn on the wafer surface. Just like developing a photo, a circuit pattern is imprinted on the wafer by spraying developer and removing unlit areas from the areas that are exposed to light. After an inspection of the wafer to check whether the pattern is drawn well, it moves on to the next step.
Okay, so I'm sure the past 1 minute maybe explained better than I said in the past 30 minutes. But if you have interest in the photolithographic, just like Jen said, we have ANFF Enlighten. On our website, there are a series of the micro nano fabrication and photolithographic online lecture. You can have a look. Thank you.
Thank you very much, Sophia. Any questions for Sophia about photolithography? Yes, up the back.
Yeah.
How does it know which pattern to follow? Is it like 3D printing? You have to design the for it to follow?
We still have to create a CAD design or create a pattern on your computer and then transfer the design to a computer. Yeah.
Great talk, by the way.
Thank you.
There was another question here.
Yeah, sorry. Really great talk. Something I was quite interested in was the use of the adhesive layer.
Yeah.
Was that
HMDS.
Yeah, so I was wondering if that gets removed along with the photoresist after it's been developed, or if that is only used in like processes where you don't want the sacrificial way for the photoresist to stay. I don't know how.
So after photolithography process, most of the time the resist will be removed. So for this HMDS, it will also be removed after the development.
Right. Right, so it comes off with the photoresist.
Yes.
Thanks.
Good question. Any other questions? Yes, Rick.
Thank you. It's a great talk. I have a question about automation of the process. I know that we are using highly sophisticated instruments, but there is great bit of human involvement involved in it. And so do you see in future we would be like, just put some AI code or whatever sort of things, and we don't need to get into the clean room and get things done. This is just a future aspect of more hypothetical situation.
You mean like automation of the photolithography process? Yeah. I know there are some equipments you can do the coating and then expose and then do the development at one equipment, really big equipment. But after that, you still need to take it out to have an inspection. So people will be like inspector.
Any more questions for Sophia? No? If not, let's thank her again. Thanks, Sophia.
Thank you.
We've got, I just mentioned to that last question, of course, The cleanliness of your lab is very important. Paul highlighted that beautifully. And we're going to put you in clean rooms in the practicals to do the prac sessions. There's a reason you're in a clean room. Of course, it's for those reasons. When it comes to mass manufacturing of microchips, a lot of it can't have humans in there. So you actually have a lot of robotics and other processes to automate. And so at the multi-billion-dollar fabs, there are not too many people in there because you're the dirtiest thing in the room. So just a bit of context there. We are going to very shortly go to lunch, but I'm just going to steal your attention for one more moment. There's been a whisper that lunch is not quite there yet. So I just wanted to come back to one thing that I didn't quite have time to go through this morning, but I'd like to just share with you to give you a bit of context. So how does the winter school fit together? You're probably getting an idea of how it fits together, but I want to give you a bit of an overview so that when you're doing certain things, you know that they're important for certain reasons. And so let me just walk you through this very quickly. This is the pieces of the puzzle of winter school. You've got insight talks, which we've already seen a few talks this morning, which are all about the big picture opportunities, careers, industry, environmental aspects around, as well as academic experts in certain fields who will give you a taste of various areas. There are lectures, which you just heard too, where they go into a bit more detail to teach you some of the aspects of things that are important, like cleanliness, physical versus chemical, depositions, as well as Sophia on the structuring of surfaces and patterning. So those things start to fit together. The practicals, of course, are to give you some hands-on. There's tours and there's networking. You'll see them in different parts of the program. Every day looks like this. In the morning, we kick off with a couple of insight talks to get you warmed up. We have morning tea, and then we've got the lectures where we'll give you a few more details. Into the afternoon, we've got some tours which are coming up very shortly, in fact. First one's to Tindo today, which I think is sold out. So if you've not got your name down, you're doing a different tour. And then coming in the afternoon, we get you into the labs to do those practicals, and as I've said before, make the most of the networking. These different elements I just talked about, but the idea is with the practicals and the knowledge that you've got, you can start to imagine, hopefully by the end of the week, if not before, what you can create, your own innovations, as Judy was talking about, that are going to change the world. Here are just a few unit operations just to help you, because you're probably seeing a lot of devices and fabrication, but we've talked about coding already, putting down materials. The patterning here is the litho that we've just, photolithography that Sophia's just talked about. Etching, where you can use patterns to then mask something that you might want to etch. You can also do direct milling and laser milling here, which will be talked about later in the school. Moulding, where you can start to replicate structures, whether it's injection moulding or the PDMS replication that you saw earlier. 3D printing, just as one example, and of course we talked about bonding. So all of these kind of unit operations that we talked about during the school, and as you can see, it's a bit of a jigsaw. Once you want to put it together in your own sequence with your own materials, you can make your own things. And so I hope that that's what you end up feeling at the end of the week you're able to do. This is just a quick different pathways, right? You can design something. You might go straight into etching if you're using a laser etch or micro machining. You might decide to do some photolithography to then mould something to then make a microfluidic device. And another example here is through to microelectrodes. And I'm just going to quickly show you two examples from your pracs. You're going to work with some electrodes that will be fabricated using this case where we put down a metal coating, we then do photolithography, and then we do etching. One click too many. Then we do etching to arrive at this patterned surface, which you can see down here. And I've put here the different lectures and the different practicals that are linked just to these, this what looks like to be a reasonably simple step. So the knowledge that you're getting this week really fits together, and I hope you'll really understand that as the week goes through. Here's a second example, photolithography, we're then moulding and then we're bonding. At the end, if I click, I think I can bond. There we go. And so this gives us our micro channels. And look here, we've got practical 1, 3, and 4, which are relevant. Lecture 2, photolithography, and packaging, which is the bonding, as well as what Michael talked about with the lab on a chip. Here's the laminar flow that you've seen before. So I'm just giving you these examples just to help your mind sort of wrap around why we're telling you all these things and in the order that we're telling you. You might find that your practicals, you might do a practical on day 1 that has some knowledge from day 3 or 4, but hopefully that just shapes it up for you so you can pull it together. The practical sessions, there are 8. They're fantastic. Don't miss them. Even if you think one's not interesting to you, get to know the people involved. The groups will be created after the industry tour. So again, hang around. Don't sort of wander off too far. After lunch, so we can get you into the groups and send you off to the right locations. A couple of tips for the rest of the week. Attend every part of every day. It sounds like I'm like a parent. Attend every day. And not doing it for me, I'm telling you to do it because I think it'll be the best way to get everything out of it because it fits together. I don't want you to miss anything, any important steps in your own fab. Introduce yourself to people, ask questions, don't be shy. Take notes about lectures, people, companies, careers. You might forget some names or faces and email addresses and things. Get to know each other and connect that way. Tell someone what you learn each day. When you get home, hopefully there's somebody you can call, text, talk to. Tell them what you learned that day because that's a great way to make sure it stays in the mind for more than 24 hours. So take home the piece from your prac and tell your mum or your pet whatever you need to tell about what you've done. This is important when you're famous because of the amazing innovations, the Googles, the Navitas, whatever you've come up with. Remember us because we want to know your stories when you get out there. So that's just a few things. Let's go to lunch and I hope you enjoy the rest of the school.
You are working on it anyway, so you get finding material.